Time to start. Quick announcements. Homework 3 is available, and I really hope you guys get started quickly on this, because homework 3 might take you some time, or it might be really easy, depending on whether you like programming more than math or math more than programming, because this has absolutely zero experiments, and it's 100% just proving things. So I encourage you to start early, because I have been told multiple times in the previous incarnation of this class that this was the most amount of work they had to put in. So please start soon. You should have started yesterday. At this point, you should be able to answer question 1. At the end of today's class, you should be able to answer question 2. And by Tuesday's class, you should be able to do question 3. And I encourage you to keep up as we go along, partly because it might be really easy or not, depending on what your background is. So in either case, take a look at it, and I encourage you to visit us in the office hours. The second thing I wanted to remind you is about the project intermediate status report, 2 pages. It's due at the end of this month roughly, and there was a question about what should be in it, and basically you need to update us about where you are in your project, and hopefully you've done more than just think about it. That's pretty much all I have with respect to announcements. Any questions? Yes?
Do you have to have a schedule, like the project
No,
schedule?
I don't care about a schedule so much as I just need to know that you are on track. So
how about the responsibility assignment? Like,
sure,
do
if you
what?
want anything that you think, you should tell me. What I want to know is how far along you've come on your project. This could be I have managed to get all the data I have, and I finished pre-processing, and I have done this little bit. It could be I finished my project and I'm going to just sit for the next 2 months, or it could be I have I have been reading these papers. I have this concrete plan of action. So take a look at the website. It gives a little bit more information on what is actually expected. But yeah, other questions? Okay. There are no other questions. I want to continue where we left off. As we were in the middle of the computational learning theory lecture, and in particular in the last class, we looked at this definition of learnability called PAC Learnability, and I'm going to just go over the definition again and continue with this idea called Occam's razor. So in the last class, we saw something called PAC learning, and in particular we saw this definition of PAC learnability, and PAC learnability is just this property of concept classes, or in fact it's a property of sets of functions. So we have a concept class C over some instance space, and we want to say that it's PAC learnable if the following large definition holds. This concept class is PAC learnable if for any function, I don't care which function is the true function in the concept class, for any function in the class, for any distribution over the data, given a finite set of samples, given m examples, using this algorithm L, the algorithm L will produce a hypothesis which is epsilon correct, whose accuracy is, whose error is no more than epsilon, and such a classifier will be produced with high probability, with probability greater than 1 minus delta. Such a algorithm such a concept class is said to be PAC learnable if all these parameters are polynomial, where m is, or rather m, the number of examples needed, is polynomial in 1 over epsilon, 1 over delta, and most importantly, in the size of the hypothesis space. this is just a definition, and we saw this in the last lecture. It's just a definition, and the important thing about this definition is whether we can show that something is PAC learnable or not. Just like mistake bound. I defined what is a mistake bound algorithm, and then went along to show that certain algorithms are mistake bound algorithms. That's exactly what we'll do now. I defined this concept called PAC learnability, and now I'm going to show how we can prove whether certain concept classes are PAC learnable or not. In addition to, just to remind you, this definition of error is error with respect to future examples. It is simply the probability that your classifier and the true function will disagree on a randomly chosen future example. In addition to PAC learnability, we also looked at something called efficient PAC learnability, which is simply another layer of complexity here, which says, yeah, sure, this concept class may be PAC learnable. There may exist some algorithm, but can you find the classifier in a reasonable amount of time? In particular, can you find a classifier in a polynomial amount of time? So the first definition talks about something called sample complexity, which is to say, is there enough information in a finite set of examples for me to recover the true function? So that is sample complexity. How many examples do we need to learn the concept? And the second definition, the efficiency, talks about polynomial time complexity. Can there be an efficient algorithm that learns this concept? And there are some minor details, but so we looked at, this is where we stood at the end of last lecture. Any questions about PAC learnability before we start talking about Occam's razor? Yes? Can you speak up?
About the error in the previous slide.
Right.
The X basically is any X belonging to the concept class.
X belongs to the instance space.
Instance space, but does it include training?
In general, there's no question about training or test. It's according to the true distribution. It doesn't matter. So there is some distribution of examples, and there's this process that keeps generating examples. Now, if I keep sampling according to that, what is the probability that your classifier will make a mistake?
You're not constraining it in any way.
No. The only constraint is that it belongs to that distribution. Yes, in fact, that's the real constraint that we have, that says that there is fixed but unknown distribution of examples. Other questions? Yes.
We make this claim, but we don't consider if the data is linearly separable or
There's no concept of linear separability here. This is just about any class of functions, about any class of instances, any data, any labeling. And in fact, for at least a large part of today's lecture, we'll only consider finite sets of functions. So linear functions are infinite. Right now we are only considered, just for this lecture, we are only going to deal with sets of functions that are finite. And then we'll move on to infinite spaces later on. Right now this is just a definition, it makes no other assumptions than exactly what is stated. Yes?
So how do you know if you have enough information in the sample?
Excellent question. That is what we're going to look at next. I didn't plant that. That was a good question. That lets me move ahead. So in fact, we're going to try to prove this. We're going to ask how many examples are needed in order to make this epsilon delta claim. And this will give us this mathematical derivation of this principle that has been called Occam's razor, which says prefer simpler hypothesis spaces. And we'll try to prove Occam's razor argument. So this is exactly where we stood at the end of last class, and I'm going to start with Occam's razor. To start this process, I'm going to prove this claim that the probability that exists. So let's consider the following setting. There is some finite set of training examples, m examples, and I don't know what the learning algorithm is, but this learning algorithm has produced a classifier that is consistent with every training example. And what we are going to ask now is, what is the probability that such a classifier that is consistent with every training example is going to have a bad error? In fact, it's going to have an error that is greater than epsilon, that's 0.2 of that. And this claim here says, such an event, that a classifier that's consistent with your entire training set and yet has poor future performance, is actually very unlikely. This event of having a bad classifier that's consistent has a probability less than the size of the hypothesis times 1 minus epsilon power n. What this means, so basically we are asking, if my learning algorithm produces a consistent classifier, can I say something about the future? And this claim says, yeah, you can. The future won't be all that bad. To prove this, what we're going to say, look at this. Let's say that there's one classifier that has one hypothesis that has this bad performance, such that it has an error more than epsilon. Some small epsilon, but still, epsilon is a parameter that you get to pick. What this means is, because the probability that it makes an error is more than epsilon, we know that it has not made an error on a particular training example, right? Because it's consistent with every training example. The probability that it is consistent with one training example has to be less than 1 minus epsilon. Why? Because the probability that it made an error on that training example would have been more than epsilon. So this is for one training example, and we make an assumption that every training example is independent of each other. So the probability that it's consistent with 2 training examples is 1 minus epsilon square, 3 is 1 minus epsilon cubed, and so on. The probability that this classifier that makes an error more than epsilon is consistent with m training examples is less than 1 minus epsilon power m. Just to put this in perspective, epsilon is a small number. Let's say epsilon is 0.1. So that's basically a classifier that is 90% accurate, or whose error is more than 10%. The probability that it's consistent with one training example is less than 0.9. The probability that it's consistent with 2 training examples is 0.9 square. If you have 1,000,000 training examples, it's 0.9 power 1,000,000, but because it's a number less than 1, it very quickly becomes close to 0. That's for one classifier. The game we play is always the same. Now we apply union bound. The probability of one classifier having this property is less than 1 minus epsilon power m. Probability that there's some classifier in your hypothesis space that is consistent and yet bad has to be less than the size of the hypothesis times 1 minus epsilon power m. Is this argument okay? Yes?
Is this hypothesis is that learner function?
I didn't get that. Can you repeat that?
Since a hypothesis set is compiled of a lot of functions.
Yes.
And this h is one specific.
Small h is one function. Capital H is the entire set.
Okay.
Yes. So that I've tried to be consistent with that notation. So small h represents one classifier. Capital H represents the entire set of classifiers that your learning algorithm considers. Questions about this claim? So what we are really saying here is, if your classifier is consistent with your entire training set, then it is, and if your training set is large enough, then it's probably unlikely that your classifier will be bad. But that's not enough, because we want to ask how many examples do we need to make a guarantee about this quantity itself. We care about this probability being low. We want to say that this probability of getting a bad classifier should be low. So let's do the same thing that we did before. Let's force it to be less than delta. Let's see what happens. What condition do we need to be satisfied if we demand that this probability of getting a bad classifier is less than delta? In other words, we're going to ask for this condition. And the rest of the game is just algebra. It's basically the same thing that we did before, and I've written it slightly differently just to confuse you. Going to take log again. So log is increasing, so the inequality doesn't change sign. And so we have log size of the hypothesis plus m times log 1 minus epsilon has to be less than log delta. And we know by definition of e power x, we know that it's greater than 1 minus x. Throw the whole thing in. So in other words, if we use the fact that log of 1 minus epsilon is less than minus epsilon, it will give us a safer bound. It will give us a bound that is weaker but still valid. So, and with some rearrangement you get, and I'm not going to labor through this, I can assure you, if you spend 3 minutes with some algebra, you'll see this point. And it's exactly the same thing that we derived for, as a special case for monotone conjunctions in the last class. What we get is, if the number of examples is greater than 1 over epsilon times log size of hypothesis plus log 1 over delta, then the probability of getting a bad hypothesis is smaller than delta. Remember that we care about what is the probability of a bad hypothesis showing up, and we want it to be less than delta. And what this condition says is, if you have these many examples, then you will get a classifier that is whose accuracy is whose accuracy is epsilon, and you'll get the classifier with probability 1 minus delta. The probability of getting a bad classifier is less than delta. Yes?
Here the capital H is the number of hypotheses that are consistent in the hypothesis space? Or
No, the entire hypothesis space. The consistency shows up in proving this claim. The probability that one function is consistent is less than 1 minus epsilon. The probability that some function is consistent is number of functions times the probability that one function is consistent. Did you have a question? Yes.
So next slide is there is like m is the number of instances with which we need to train. But unless and until we train the classifier and test it, we won't be able to determine epsilon and delta. Right?
Oh, that's an excellent point, actually. In fact, yeah, that's a very good question. So, sure, this is nice to have, but in practice, you don't have a choice over how many training examples you have. You have a training set. You have a certain number of examples. What this tells you is that with that finite training set, and if you require that your classifier should have an error epsilon, what is the confidence that you can in your classifier? Or alternatively, you have a finite set of examples and you demand a certain confidence in your training procedure. What's the best accuracy you can guarantee? So there are 4 things that you can plug in here. There's m, epsilon, delta, and the size of the hypothesis. Typically, size of the hypothesis is fixed because your learning algorithm searches over a certain hypothesis space. So there are 3 things in play. The size of the training set is fixed because you only have the data you have. Now you can trade off epsilon against delta.
You can choose the hypothesis space accordingly, right?
Yeah, you can, but often yes, you can, but quite often you don't have the liberty of doing that because certain hypotheses, we'll get to this in a minute. But I'm going to claim that this statement here is actually a mathematical formulation of Occam's razor. And let's see what these different pieces mean. First of all, if I demand that the error should be low, that is epsilon is low, 1 over epsilon becomes high, so what we need more examples. If I need small error, I need more training examples. So the sample complexity increases if you demand that your classifier should be very, very good. Which is kind of intuitive. If you want a good classifier, you need more training examples. The second one is the size of H. If you have a small hypothesis, or in fact if you have a larger hypothesis space, that increases sample complexity. We've been talking about this multiple times. So in the beginning I told you that search over the large hypothesis space is futile because the search space is going to be large. This is a mathematical formulation. Prefer smaller hypothesis spaces. Because if you demand complexity, if you demand really big functions, really complex functions, size of H becomes big, which means the number of examples you need becomes very big. The third component is delta. If you want a higher confidence in your training procedure, then you need more examples. The sample complexity will be higher. Now, the coolest thing about this whole formulation is I made no assumptions about the learning algorithm. The only assumption I made is that the learning algorithm produces a classifier that is consistent with your training set. Can you tell me a learning algorithm that produces a consistent classifier? We've looked at one, at least one. Someone whispered an answer here. Decision trees. The decision tree learner will produce a decision tree that's consistent with your training set. Now we have a version of some theory that says, if it's consistent, can you actually believe the tree on future examples? Questions? Yes?
It seems that this wouldn't hold true if there were noise in the data.
That's a bit of a straitjacket that we put on ourselves. For now, I'm assuming that there's no noise, and no, actually not noise. For now, I'm assuming that there is the assumption of this consistency. The noise, on the other hand, is slightly different because I've made no assumptions about the concept space here. Noise can be seen as either noise or it's just this complicated function. And I've made no assumptions about it. If it's consistent with the noisy data, it's still consistent with the data. We are not hoping to get a perfect classifier because they are allowing for the error of epsilon in the future.
How can we apply this to decision trees? Because decision trees don't assume a distribution over the data.
That is right. There is one. We don't assume one. Decision trees don't assume. The algorithm itself does not assume a distribution of the data, but if you want to analyze the algorithm and produce an epsilon delta guarantee, then you can start thinking about it. In fact, your homework makes you think about the a limited version of this decision tree learner called decision lists. And I asks you to quantify the performance of decision lists, irrespective of what the learning algorithm is. Yes.
How do we reconcile Occam's razor with the example that we looked at maybe a couple weeks ago with, I think it was K disjunctions or conjunctions, where there was a disadvantage at looking at a smaller hypothesis space because of the complexity and
Right.
look at a more general.
Yes, in fact, that's an excellent point. The disadvantage of looking at a smaller hypothesis space. So let me repeat the question. Maybe a few weeks back, we looked at a class of functions where there was a theorem that said if you search within the class of functions computationally, there's no way you can find a good one. That was a computational complexity issue, not a sample complexity issue. This theorem says nothing about computational complexity. It says nothing about whether you can find the classifier. Efficiency is another layer that's needed on top of this. This is necessary but not sufficient. And in fact, I'll repeat that point maybe in about 30 minutes. Yes.
I have the same question with him. Can we just see this generalization about the conjunction?
It is actually.
But conjunction is n over x.
Yeah, it's not exactly the same.
So
Yeah, in fact, if you directly plug in that, you'll not get the same bound.
yeah, why is different?
Because there we proved that's a slightly different bound that we use. This is a weak bound.
Okay.
We can get something better than this
Okay.
or larger than this. That was just an example of can there be PAC learnable algorithms. This is that assumes that if we are sitting on conjunctions, this is in general.
So,
One of them implies the other actually. I think that implies this.
so that one is tighter than this one.
I should think about this. I think this is actually even tighter. This may be tighter. I have because that was an n log n dependency. and this will give us just a log n dependency. Yes.
So just one more comment on what I just said a second ago. So it's almost like, from this perspective, you want to favor a smaller hypothesis space, but with the time complexity, you want to maybe fall in some cases.
Perhaps.
Yeah, and so you have to kind of find some kind of balance.
Yes, and this again brings us back to this old question of how do you pick a hypothesis space? Can we get a good hypothesis space that is general enough to represent what we care about, easy enough to search that we can find something good, and yet not so large that it can express everything. And somewhere at the bottom of all this, we'll get back to linear classifiers. Other questions? Yes?
How does it relate to overfitting? If the H size is very large, what will happen?
If H is very large, this is simply saying, let's see. Then you have to trade off, basically swap M and epsilon. Epsilon will be greater than log H divided by M. So if your H is very large, your error is going to be large. Yes?
What if you had hypothesis spaces and algorithms that didn't converge to hypothesis elements uniformly? Meaning, inside of your hypothesis space, you bias towards
certain kinds of
certain.
Right. This is a very weak bound. There we've applied the union bound here because it's completely agnostic to the actual bias over hypothesis spaces.
This is like it's equally probable to choose any.
If you know something else, then you can kind of tailor this bound to, you can tweak this, and people have done that. Yes. Excellent questions. Let me move ahead. So I mentioned this earlier. This is called Occam's razor because it tells us that smaller hypothesis spaces are better. And there's another way to think about this. Basically, it shows when a consistent, we made two assumptions here. We made an assumption of same test train distribution and consistency. There is some procedure that finds a consistent classifier. But another way to think about this bound is if there's this large, it does not necessarily say that picking a large hypothesis space is always bad. All it says is that smaller hypothesis space are less likely to, in some sense, fool the learning algorithm by being consistent with many, many examples. Because there are so few functions in a smaller hypothesis space, and yet if there's an element of that is consistent with many, many training examples, it's unlikely that that function is bad. Doesn't necessarily mean that every large hypothesis is bad. There's a subtle distinction here. That make sense? If a smaller set of functions is consistent, it is unlikely that it's just by chance. So this gives us, so how do we use this? How do we use this recipe? First of all, it gives us a way to test PAC learnability of concept classes. What we do is, simply, we go and find a hypothesis that's consistent with your entire training set. Just go and search. And what this bound tells us is that if the number of examples is large enough, because your function is consistent, it's probably close enough to the true function. Another way of thinking about it is, even before you search for these functions, you check, is my hypothesis space so large that the number of examples I need to make any kind of guarantee is exponential? If that's the case, there's no hope. And in fact, that's how most of the time we'll apply this bound. But that's not enough, because we also need to actually find an algorithm, because it's not enough to just say that some of these many examples are needed. We are in computer science, so we care about computational complexity. So we need to do two things. First, count the number of hypothesis functions in the space. How many functions are we searching over? Plug it into this thing and ask whether you need only a polynomial number of examples or an exponential number of examples. The second thing you need to do is produce an algorithm that can actually do that search. And that algorithm should be polynomial. So there are two things that should be polynomial, number of examples and the algorithm. And I'll show you some examples of all these, how these things work out. I just want to remind you that, as you pointed out, we worked out these details for the case of conjunctions. Conjunctions are PAC learnable because it turns out that it obeys the sample complexity bound, and there is a rather simple algorithm called elimination, which is O of n if you have n-dimensional conjunctions. So it's polynomial in the size, in the number of, in the dimensionality. So conjunctions are PAC learnable and they are efficiently PAC learnable. Questions? Yes.
We're only showing lower bounds for m though, right? And we don't need to have an upper bound to prove that it's PAC learnable?
No, we just need to show that we need at least these many examples. So the PAC learning definition is exactly this. It says that if you have these many examples, then life is good. M should be polynomial. Yeah, you're right. The other side of bounds are actually much harder to prove.
Because wouldn't we have to say, like for the elimination algorithm, we showed that actually we need to have at least that certain number of examples in order to...
Yes, exactly like this.
Yeah. But don't we need to say that at most?
No, well that's a much harder statement to prove typically. Upper bounds are difficult. This says if you have these many examples, then the error will be okay. Yes?
If the hypothesis size is very small so that it cannot be able to denote the function.
We are assuming that there's one function that's consistent.
Okay.
So at least for now, we are assuming that there's a function in the hypothesis space that is consistent with every function in the concept space. Just for now. We'll drop that assumption maybe in about 30-40 minutes. But for now, we are assuming that that's what gives us consistency. Yes. So as an exercise, this may not be the most obvious thing, so I encourage you to go over this and work out the proof just to convince yourself that I'm not lying. And think about decision trees. Think about whether decision trees are PAC learnable. I'm going to show you some examples of positive and negative results from this theory. And you can apply similar ideas to arbitrary decision trees just to see if it works. So, if there are no questions about sample complexity bounds, let's start applying this bound to different concept classes to see what happens. And for now, I'm assuming the concept class and the hypothesis class are the same. We just are, they are the same set of functions for now. The first thing that we saw, this is just a different version of something that we already saw, conjunctions are PAC learnable. Why? Because, as I hope most of you now agree, the number of conjunctions with n dimensions is 3 power n. So we can just plug it into that formula there. The number of examples you need is 1 over epsilon times n log 3 plus log 1 over delta. So really, the complexity parameter here with respect to the hypothesis class is log of the size of the hypothesis class. So all we need are a linear number of examples, roughly, in the dimensionality. So the way to apply this is, if you want a guarantee that there's a 95% chance of learning a hypothesis that is at least 90% accurate. You care about getting a function that will make errors less than 10% of the time, and you want to find this function, you want a guarantee that you will find such a function 95% of the times. Then with 10 variables you can just plug this in and you need 140 examples. You need more than 140 examples. At least 140 examples. If the dimensionality increases tenfold, roughly the number of examples also increases tenfold because it's linear. if you increase your confidence from there to, instead of 5% error, you want 1% error, or 1% chance of finding a good bad, or 99% chance of finding a good classifier, then it increases just a little bit more. So you can, because it scales logarithmically with delta. So this could be one way of asking how many examples you need. If you have 100-dimensional Boolean functions, how many examples are good enough? So for example, say I want to build a spam detector, and I believe that my email is spam. Whether my email is spam or not is simply a conjunction of some features. Then I can ask, and let's say the number of features we have is, let's say 1 million. Now we can ask how many examples do you need? You need roughly 1 million examples, or actually more than that, but you need those many examples to get any kind of guarantee. Questions? Yes?
Something that's troubling me. Let's say that your concept, like you have a concept class of conjunctions. Let's just say that that's just flat out wrong. And does this guarantee basically just go away then?
Yes. We'll see other guarantees that now come into play afterwards. Where you make, so right now we are still in this little sandbox where we are assuming that the hypothesis class is the concept class, and that the hypothesis class is finite. At the end of this entire chapter or section, we'll drop all these assumptions. We'll go to infinite hypothesis spaces, and we'll consider the case when there's no function in your set that is good enough. Actually, it turns out roughly similar kinds of guarantees exist. So basically, what that says is machine learning is not impossible in certain situations. Notice I've done something else here, which is, or rather, there's something I've not spoken about at all, which is in this analysis, I've said nothing about the learning algorithm. This works for any learning algorithm that can produce a consistent hypothesis. It could be the stupidest algorithm which basically lists out every conjunction. It doesn't matter. It works for any learning algorithm that is consistent. On top of this, we care about actually getting good learning algorithms as well, but as far as this analysis goes, it's orthogonal. Okay, let's take another class of functions. And now I'm going to very quickly ramp up the complexity of these functions, and I'm going to, the next maybe 10 minutes is going to be a laundry list of different classes of functions. So 3 CNF, 3 conjunctive normal forms. Just to remind you, it's a subset of all conjunctive normal forms where every conjunct, which are these blue boxes here, contains at most 3 literals. So literal can be a binary, a Boolean variable, or its negation. So you have L11, L1 and L2 and L3, or L4 and L5 and L6, or and so on. So let's start this process of analyzing this class of functions. The first step you need to do is to ask yourself, well, first of all, what's the sample complexity? That is, if I had a learning algorithm that produced functions consistent with this, that can produce functions that are consistent with the training set, how many examples do you need to get the epsilon delta guarantees? To do that, we can use that bound that we derived, and really the only piece of that that depends on this the function class is h, the size of h. So really all you have to do is count the number of functions. So what we need is the number of 3 CNFs. Quickly, how many 3 CNFs are there?
Well, how many variables are there?
N.
They can appear more than once.
Yes. Let's try to derive this. First of all, let's break this up into pieces. The number of unique 3 conjunctions is 2 power n cubed. You have 3 slots. Each slot can have, you have You have 3 slots. Each thing can accommodate either xi or negation of xi. And there are 2 power n such things. Sorry, there are 2n such things, because you have n variables, you have n negations, so the total number is 2n. So you have the number of conjuncts is number of possible such things is 2n cubed. Okay? Yes?
I thought you said at most 3 literals, so it can't be xi negation or true.
Yeah, so this is just an order, this is a back of the envelope kind of calculation. There are subtleties, but this is a much bigger number than that. Oh, actually no, this is roughly the same order of magnitude. There will be a few more because you'll have pairs and single things as well. But this is the order of magnitude of that. Okay. Now, once you have these these conjuncts, a 3CNF is simply a conjunction of these things, right? So you have something here, something here. Oh, I made a mistake. This should be an and. So you have basically a conjunction of many things. So what we want is how many conjunctions are there with these many elements, with these many variables. How many conjunctions are there with, how many monotone conjunctions are there with n variables? This may have showed up in your exam. May have, I don't know.
Was there n terms in the conjuncts, and then there's m conjuncts, and you have n, so that m, right?
No, but you have, forget this whole thing. You have n variables, and you want to build monotone conjunctions. How many monotone conjunctions are there?
So you choose something. Oh, 2.
NC3?
There's no 3 here. We're not talking about 3 CNFs.
So 2 to the power n.
Why is it 2 power n?
Because you're choosing a subset of the variables and making those into the conjunct.
Yeah. Another way of thinking of it is you're going to build this giant conjunction. In every case, with n, you have n slots to fill because you're going to put an and between all of them. You have n slots to fill. Each slot can either get a variable or not. You have n slots. There are 2 options for each slot. So it's 2 power n. If you have n variables, there are 2 power n monotone conjunctions. A 3 CNF is simply a conjunction, a monotone conjunction of these things. And there are these many of those. So the number of 3 CNFs is simply 2 power that number. That make sense?
So how do we know that there are n spots to fill?
There are not n spots. There are these many conjuncts that we can in the bag, and we are going to create a conjunction out of those things. Because a 3 CNF is simply a big conjunction. It just so happens inside each the variables of the conjunctions are not variables, but themselves something more complex. We don't have n spots to fill, we have 2n cubed spots to fill. The bottom line is the number of 3 CNFs is roughly 2 power n cubed. And log of that is roughly n cubed. So we can plug this in. Log of the size of the hypothesis space is n cubed. So how many examples do you need to learn a 3 CNF? It's cubic in the dimensionality. I can simply plug this expression into the bound that we derived. The log of the size of the hypothesis space, this is the most important refrain here. the log of the size of the hypothesis space is polynomial in the dimensionality, which means the sample complexity is polynomial in the dimensionality. So 3 CNFs are PAC learnable. So what we have proved here is that the concept class of 3 CNFs is PAC learnable. I just created a new class of functions. I know nothing about this. I haven't even thought about a learning algorithm, and yet I can say that this class of functions is can be efficiently represented using a small number of training examples. In this case, cubic, which is kind of cool. I don't know about you, but I think this is really cool. But I'm trying to think about learning algorithms, and the first thing I do is not think about learning algorithms. Think about whether learnability is possible. Of course, we still have to produce learning algorithms. It turns out we need an efficient learning algorithm for 3 CNFs, and I'm going to leave that as an exercise. Try to come up with an algorithm that will find a 3 CNF if the data is produced using a 3 CNF. Hint, it will look a lot like the elimination algorithm, because this is still a conjunction, right? It's just a big conjunction. So questions about this kind of analysis, because you'll be doing a lot of this. Yes?
In this question, variable can only appear once, or it can appear many times?
It can appear multiple times across different things. Yes. Other questions?
So this is kind of interesting. I mean, it kind of reminds me of like
I agree.
Sorting, in that like sorting, you have a lower bound for
Yes.
the complexity.
Yes, yes.
And so
In fact, exactly like that. I mean, if you know the history of this, you can prove that there must be an n log n fault sorting algorithm, even without thinking about algorithms. And then, just so happens that merge sort exists, but we can prove that there is enough information. But this is not proof that there exists an algorithm, because it's possible that there may be enough information, but the search is a different story. And in fact, I'll show you an example of a class of functions, another class of functions where sample complexity is polynomial, but time complexity is not. Or at least I'll tell you about a class of functions. Okay, let's take one more example. Arbitrary Boolean functions. How many Boolean functions are there? Yes.
2 to the n?
Yes. You have 2 to the n Boolean functions. And does anyone see a problem here?
It's a lot.
It's a lot, but with respect to sample complexity.
The log of that is still
The log of that is still exponential. So log of size of hypothesis is still exponential because it's still 2 power n, which means the number of examples you need is still exponential. So here's a class of functions that are not PAC learnable. General Boolean functions cannot be learned. I gave you kind of a fuzzy intuition early on because just said that there are so many functions, but this is a more information theoretic argument. In order to learn a general Boolean function in n dimensions, you need of the order of 2 power n examples, at least. Which doesn't work if you have 100 features even, or if you have 1,000,000 features, good luck.
Well, 2 power n, that's all of them, right?
Yes, exactly.
There's no learning.
There's no learning. So this is an example of a class of functions that are not PAC learnable. Questions?
So what you might want to do is, basically the moral of the story is that you should know something about it so that you can restrict it to some subspace that is PAC learnable.
Yes. In fact, that's the model of this whole semester. You need to know something about your class of functions. You need to make an assumption about your class of functions so that learning is possible. unbiased learning is a hopeless adventure. Okay, couple of more examples about sample complexity. This is just, I'm going to throw this here, and you can come back to this and look at it yourself. We looked at 3 CNFs. K CNFs are PAC learnable. Here's just a bunch of functions that are PAC learnable. 3 CNFs are PAC learnable. Something called K clause CNFs are PAC learnable, where you have at most K different clauses. In 3 CNFs, you had something like L1 and 2. And so on, where each term here can have only, I think I've switched, this is a DNF, but it doesn't matter, the argument is the same. Each block here can have only 3 elements. A K clause CNF simply says there are only K clauses, each clause can have an arbitrary number of variables. Similar sort of a counting argument, it turns out it's also it's easy to prove that it's PAC learnable. K DNFs. DNFs are the disjunctive versions of the CNF, they are also PAC learnable. K term CNFs are PAC learnable, but it turns out, I'm not going to define these functions. I expect you to just go back and look them up and see what they are. I just want to point out that we know a lot of sets of functions that are PAC learnable, and we can actually prove, and maybe you'll prove in an exam, maybe, that they are PAC learnable. But the point is, say I want to learn, say, this class of functions, K-term DNF, a 2-term DNF. What should your hypothesis class be? So, suppose I produce a data set and I give it to you, and I tell you, this data set comes from this class of functions that's called a 2-term DNF. There are m examples, it's PAC learnable, so I'm giving you enough examples that meets that bound. Now, as a person who's going to now design a learning algorithm, you're convinced, first of all, that I'm not asking you to do something impossible, because it's PAC learnable. So now, you have to come up with a learning algorithm. So to come up with a learning algorithm, the first thing you do is to pick a hypothesis class. You know that the concept class here is 2-term DNF, because I told you. So what hypothesis class should you pick? There's a class of functions, and I tell you that I've got a hidden function that belongs to that set. And now you have to invent a learning algorithm to find that function. What set will you search over? And I tell you the name of that set.
You just choose the same set?
You can choose the same set. You can say that I want to search over the class of whatever that is, 2-term DNFs. And that's where I tell you that computational complexity is going to hurt you. Sample complexity is good. It turns out for this particular class of functions, a 2-term DNF, looks something like this. You have 2 blocks. So let me go back here. So you have something or something else, and each of these can be A and B and C, D, something like this. There are 2 blocks. It can either, all these the first set of variables should be true, or the second set of variables should be true, but there are only 2 such sets. This is a 2-term DNF. It turns out the computational complexity for learning a 2-term DNF is not on our side. It's NP hard, computationally. So from a sample theory, from the sample complexity point of view, the K-term DNF, a 2-term DNF, is PAC learnable. From a computational complexity point of view, a 2-term DNF is not. So it's not efficiently PAC learnable. And it turns out, okay, this is a point that if you get it, I'm happy. If not, think about it. It turns out that we've seen an algorithm for KCNFs, elimination workers. And It also turns out that every two-term DNF is an instance of a KCNF. So we can create, and there's a standard reduction, and I encourage you to go over it. I'm not going to discuss this in too much detail, but the primary point is we have an algorithm to learn the set of KCNFs. We know that every k-term DNF is a KCNF. So what we'll do is just search over this larger set. So the picture of this looks like this. There's a function. It belongs to some concept class, in this case 2-term DNF. And we know that searching this set is prohibitive computationally. We also know that this set is actually a subset of a larger class of functions. And we know how to search that larger class of functions, which is kind of, to think about it. Searching over the larger space is easier, it turns out. So what we'll do is just change the representation. We'll go to the larger space and search for functions in that larger space. This often happens. You may have to, think of, you may find that certain representations, even though they are learnable from the information theory point of view, from the sample complexity point of view, they are not learnable from the computational complexity point of view, so you pull this trick. You find a larger set of functions which are easy to search and show that this set that you care about is a subset and search over the larger set. We've already seen this before. Where have we seen this before?
AK disjunctions or whatever it was we would see.
Yeah, so linear classifiers, in fact. There were all these functions that it turned out many functions could be represented by linear classifiers, and here's another motivation for using linear classifiers. A, we know there are good algorithms for this, and B, they represent so many interesting things, might as well search over them. Search over these the class of linear classifiers. Another class of negative examples, there are two. So basically, there are two ways in which learnability can be prevented. The first, one way in which functions cannot be learned is from the time complexity point of view. Basically what we'll do is we'll show that certain classes cannot, because there is no algorithm that can search over this class of functions, or no efficient algorithm. Effectively, this kind of a proof becomes, we cannot find a k-term DNF unless p equals np. At that point, all arguments stop. So this is one class of impossibility results. And this is the kind of impossibility that we are kind of familiar with in computer science. Certain things are just not computationally possible. In the machine learning universe, we get another kind of impossibility, which is sample complexity, which is information theoretic. It says, with only a polynomial number of examples, this concept class cannot, two functions in this concept class just cannot be distinguished, because there is not enough information in only a polynomial number of examples that can let us tell apart two functions that are close to each other. So this is the this is the PAC argument. And the second class of, I expect that most of you have seen the first kind of result at some point before in your life. Certain kinds of things are not computationally possible because the time complexity is prohibitive. I'm not sure, maybe most of you have not seen the second kind of an argument, which is saying that there isn't enough information in this finite set of examples, in such a small set of examples, that can tease apart functions from a set. Yes?
Would an example of the second one be like if you were running a simulation and you discretize your space? If your discretization isn't small enough, then it won't converge. If it's like an iterative thing, is that kind of like the sample complexity?
I have to think about this because I'm not. here the set that we care about is a set of functions actually. So the classic example here is actually the Boolean set of all Boolean functions.
Right, but the first one doesn't have to necessarily be tied with machine learning. That's just computational complexity. But
the second one actually, the classic example there, as I said, is Boolean functions. If I give you 2 power n minus 1 examples, still not enough information because that last example may be needed to tell apart 2 Boolean functions. So that is not enough information in so many examples. Other questions? Yes.
So with the prior slide, if we expand the hypothesis space, does that mean that we need to increase the sample complexity?
Perhaps we might. In fact, that's the trade-off. On one hand, learning is impossible. On the other hand, learning is possible, but we need more examples. I would rather pick possible. So, just to throw out a few sets of functions, K-term DNS cannot be learned from the computational complexity point of view. 2-layer neural networks cannot be learned of certain architectures from the computational complexity point of view, which simply says you need an exponential number of examples. A class of functions called read-once Boolean formulas, which I have only seen in machine learning papers, probably they were invented just to show that they cannot be learned, if you throw in quantifiers like existential or universal, for all or there exists, those kinds of formulas cannot be learned. All of these are complexity point of view. From the information theory point of view, from the sample complexity point of view, arbitrary Boolean functions, as we just saw, cannot be learned because you need an exponential number of examples. Finite state machines cannot be learned, context-free grammars cannot be learned. So basically, there is a lot of impossibility here. So it's all gloom. Of course, remember that we are putting ourselves in this really constrained setting where we demand that the hypothesis space should contain, for every function in the concept space, there must be one function in the hypothesis space that is consistent. So we are demanding consistency here, right? And that's a pretty strong requirement. We want our classifier to be consistent with every single training example. What if there's one training example that's just too difficult? There are 1 million examples, and one of them, I can't find any function that is consistent with all 1 million, but I can find a function that's consistent with all but one. 1 million minus 1 is large enough. So maybe I can give up this consistency a bit and try to build an argument around inconsistent but almost correct learning algorithms. Is the difference clear? Is the point about consistency, does that make sense? So this takes us to this class of, so just to step back and see where we are still in computational learning theory. So we looked at this definition of learnability called PAC learning, which is not an unreasonable definition, and it talks about how many examples do we need to ensure that some learning algorithm will be able to find a classifier. And PAC learning made 2 assumptions, or at least the first iteration of this process, we made 2 assumptions. Assumption number 1, all examples, both the training and future examples, are drawn from the same distribution and are independently sampled, IID. And the second assumption we made is there is some learning algorithm that will find a consistent classifier with the entire training set. Right? And we also made a third assumption, which is our hypothesis space is finite. So there are 3 assumptions in play right now. We're going to drop the first one of these assumptions, this consistency. And this gives us this setting called agnostic learning. So this is still batch learning, and PAC learning, at least the version of Occam's razor that we saw so far, asks how good is a classifier on future examples if it's consistent with your entire training set. And even there we can kind of prove interesting things. So the question is the second assumption reasonable? Is this assumption of consistency reasonable? Is it?
Get overfitting.
You get overfitting. Decision trees overfit. Maybe consistency is too strong. Maybe consistency forces you to fit even noise in the training data. Because if there is noise, you still demand that your learning algorithm should explain that noise. So let's drop that. Another way of thinking about the same picture is we are asking for something like this. For every function in the concept space, there is some function in the hypothesis space that's equivalent to that function. What if we want to learn a concept f? That concept is in some concept space, but there is no function in your hypothesis space that completely agrees with it. And this is a more reasonable setting because, we never know what the concept class is. Because we don't even know what the true function is, so we have no hope for knowing what the concept class is. So assuming consistency is unreasonable, so can we drop that assumption and prove any bounds? Does this setting make sense? What will the training error be in this case? First of all, what's the training error? What's the error on the training set in the consistent case? 0. Because your classifier that the learning algorithm produces is consistent with every training example, which means it correctly labels every training example, which means the training error is 0. If we drop the consistency assumption, what about the training error now? There is no function that is going to produce the same label as for every training example as the original function. There's no function in your hypothesis space. What's the training error now? It can be greater than 0. It may be 0 if you're lucky, but it can be greater than 0. So it's no longer guaranteed to be 0. Because there's no consistent function. So now, we can now slightly shift our goal. What if I try to minimize training error? So now the job of the learning algorithm is not to find a classifier that has 0 training error, but has as low training error as possible. Just to remind you, the training error is simply the training error of a hypothesis is simply just take your training data for every example, use your hypothesis to predict a label, and see how many mistakes you make. So the number of mistakes divided by the size of the training set is the training error, the fraction of training examples that are mislabeled. So this is not guaranteed to be 0, so what if we try to minimize this? So can we get a guarantee that says a hypothesis that has a low training error will also have low generalization error? Because remember, that's really the point of learning. The goal of learning is to make few mistakes, small number of mistakes on future examples. So we want our learning algorithm not to perfectly predict the training set. It will be nice if it does, but we care more that the the hypothesis the classifier that it produces does well in the future. So the game we are playing now is you learn a classifier, it has some training error, and is there any connection between a low training error and a low generalization error? Can we say something about the connection between these two things? And now this takes us, is the setting clear? Are there questions about the setting first before we get into the math? Ask me questions. And is the difference okay? Yes.
We have to have some intuition on how much the misclassification rate would be in order to apply this?
On future examples?
In the training of itself. we talked about potentially overfitting the data. And
Yes.
if we believe that we're looking for some error, but we're saying we're expecting some misclassification when really there's a lot more,
Yeah.
that can cause the same problem or overfitting.
Yes. Yes. Yes.
So do we need to have some intuition of what our max bound of misclassification would be?
That's roughly the right intuition. Effectively, what we want, the assumption that we have, remember the key assumption that's still in play is that the future still will look like the present. If you make a small number of mistakes now, maybe you'll make a small number of mistakes in the future because the examples are drawn from the same distribution. And that's the only assumption that we still have. Actually, we have two. We have that and the finite hypothesis space. But yes.
So I was under the impression that overfitting was only really a problem if we have noise. If we have like a biased training sample. Can you explain like why we wouldn't want to
Overfit even in the absence of noise?
Yeah.
Let's say there's no noise, but your true function is a really, really complex function. Okay? And that means that you have to search over a really large and complex set of functions.
That means your sample's not going to be large enough to like
Exactly.
get you.
So you might, instead of that, you would rather search over a smaller set of functions, guaranteed to be wrong in at least some cases. But can you find a small enough set that is at least okay?
So we would generally use this when you decided that your function is so complex that you
Yes.
don't have
In fact, you can think of noise as just a complex function, right? You don't know. In fact, in the absence of any information, you don't know if it's noise or just a complex function. When you are completely, at least from the theoretical point of view. So to analyze this kind of stuff, and I see that we are quickly running out of time, so I'm going to start this analysis and point you to the kind of mathematical tools we need, and maybe you can go back and over the weekend refresh yourself on these things so that the next time you can prove it before I do. So in order to make any kinds of statements about the connection between the training error and the generalization error, we have to start thinking about tail bonds. At some point, I hope, all of you have seen tail bonds. Simply asking, how far away can a random variable be from the mean? What? What? Well, that's one version, but there are many, many, many theorems around this. But simply what we are asking is, so you have some probability distribution, what fraction of it lies in the tail, far away from the mean? And I'm sure in grade school all of us have looked at probability inequalities. This is just a refresher. There's Markov inequality that says how far can a non-negative random variable, how much more than some constant can a random variable be, and it says that it can't be, there are standard bounds. There's a Markov inequality, and you can use the Markov inequality to prove another bound called the Chebyshev inequality, which says how far can a random variable be from its mean, and it says that it can't, the probability that a random variable is far away from the mean, probability that x minus mu is greater than k sigma, has to be very small. It doesn't say, notice that this says nothing about the empirical mean versus the expected mean, the empirical mean versus the actual mean. It just says, if I have a random variable, I don't know what distribution it is, it won't be too far from the mean. And the probability that it gets farther away from the mean gets smaller as you go farther away. But we care about learning, so what we want is, we want to bound sums of random variables. What we want is really, so you can think of training error as a random variable, or you can think of the error as a random variable, and the training error is simply the empirical mean of such a random variable. So let me give you an example of what I'm talking about. Basically, the kind of bounds that we we will be using come from, or at least in the class next week, I'll be using this thing called the Hafting inequality to derive a version of Occam's razor for this agnostic setting. What we have is, we have some random variable, P. Let's say P is the expected mean of that random variable. So for example, I have a coin toss, P could be the probability of seeing heads. And let's say you toss the coin 100 times and you count the fraction of heads, and we'll call that P bar. That's the empirical mean. And this inequality says the probability after 100 examples, the probability that your empirical mean will be more than epsilon away from the expected mean has to be less than e power m, e power minus m, e power minus 100. So if you toss the coin one time, maybe you'll be the mean might be 5. In fact, it's guaranteed to be 5. If you toss the coin 100 times, it simply says you very quickly converge into the mean. And the convergence rate is actually very fast. It's e power minus m. You may not have seen Hafting's inequality before, but it's the idea, okay. Questions about this? Yes?
Does P have to be a binomial expected value? Could it be?
In fact, we will be using binomial because the error is binomial.
Yeah, in that case, in this class, it's probably what we're interested in, but in general.
In general, we can prove this is a general class of inequalities called the Chernoff-Hafting inequalities, and we can prove other such things. And in fact, the difference between the Chebyshev inequality and Chernoff is simply here we get convergence rates. How quickly does the thing converge? If you have m trials, if you have one trial versus 10 trials, how quickly do you get as the number of trials increases towards the mean? And Hafting's inequality says for a binomial random variable, you'll very quickly converge as the number of trials increases. So I'm going to stop now because I don't want to start a new proof, but please go over these kinds of, if you've not seen this before or if you've seen this before maybe 20 years back, please just take a look at it again because I don't want you to be blindsided. And at this point you should be able to do question 2 in your homework, so take a stab at it.